All right, we'll continue with our study of these variational principles. What we did in the previous segment was obtain the condition for equilibrium in nonlinear elasticity. And we did this by going back to segments even before the last one. We did this by starting out with the functional, the free energy functional. We used our notion of a variational derivative that we'd developed previously, and we applied this idea of extremization of that variational derivative. Okay? What all of that brought us to was the following condition. Okay? So, the equilibrium condition for nonlinear elasticity. Okay? It is the following. For all W, which are variations belonging to V, and we remember what is special about our space V. It consists of functions W such that W equals 0 on that part of the boundary, the displacement boundary. Okay? So, the equilibrium condition is that given any function W which lives in the space V, that means it has to satisfy the homogeneous displacement boundary condition, we have integral over omega naught first Piola-Kirchhoff stress P contracted with the reference gradient of the variation W integrated over the body, or integrated over the volume, minus integral over omega naught, the body force defined per unit reference volume dotted with the variation integrated over the volume, minus integral over the traction boundary, traction dotted with W dA equals 0. Okay, some things to note. We have tensors showing up here as well as here. We have vectors elsewhere. However, this equation finally is a scalar equation, because every tensor is contracted out with another tensor and every vector is being dotted out by another vector. Okay? Now, this form of the equation, or this condition, is also often called the Euler-Lagrange equation, or the Euler-Lagrange conditions, of the functional. Okay, and we note that these are conditions of equilibrium. These are extremal conditions upon the functional. Okay. Okay, and at the end of the last segment, I also said that this equation, this integral equation, also is referred to as the weak form of the balance of linear momentum for static problems. Okay, this is also the weak form of the balance of linear momentum for static problems. Okay, what we're going to do now is work with this integral form a little more. In particular, we're going to try to understand why it is called the weak form. And as you might imagine, we are actually going to come up with the strong form. And that strong form is going to look very familiar to you. In order to do that, we are going to resort to an old trick in calculus, especially in integral calculus. We are going to invoke integration by parts. Okay? And in particular, we are going to apply integration by parts on this integral. Okay? So, we are going to go to another slide, and we are going to apply integration by parts. Okay. And in particular, we're going to apply integration by parts on the following term. Integral over omega naught P contracted with this reference gradient dV. Okay? Now, what we're going to do is the following. I'm going to actually write the rest of the equation so we can see everything coming along for the right. Okay? So, we have this first term, and let's also include the remaining integrals which make up our equilibrium condition. Minus integral over omega naught Bf dotted with W dV minus integral over the traction boundary T dot W dA equals 0. Now, we're going to apply integration by parts only to the first term because that's the one involving a derivative on the variation. Okay? Right? Okay. So we apply integration by parts, and the way this works is the following. Essentially, integration by parts tells us that that term can be written as follows. Right? It is integral over omega naught, okay, of the following. Divergence of P partial derivative of W with respect to x. Okay. Let me do this a little differently, actually. Sorry, I'm going to back up a little here. I'm going to directly apply the integration by parts formula. Okay? So that turns out to be minus integral over omega naught divergence of P, okay, divergence of P dotted with W dV plus integral over the boundary of the domain of P, okay, P dotted with P acting upon W, the whole dotted with N dA. Okay? The other terms just come along for the ride. In particular, we have integral over omega naught Bf dotted with W dv minus integral over the traction boundary t dotted with w dA equals 0. Okay? What we've done here is simply apply integration by parts to the first term in that equation, okay? And it gave us those two. All right? The way to think about this, if you're not familiar with applying integration by parts over tensor fields, the way to think about it is to realize that integration by parts really consists of two steps. One is the product rule of differentiation, right? And the other is the Gauss divergence theorem. Okay? And what I'll do here is very quickly show you how that works. Okay? So the reason that works, the reason we can go from this step to here, okay, or we could go backward as well. The reason we can do that is because okay, or because of the product rule of differentiation and the Gauss divergence theorem. All right? Let's see how that works, and in order to work, I will actually use coordinate notation. Okay? So, integral over omega naught, what we are trying to do there, and that with that very first term at the top of the slide, is the following. P little I capital I partial of W little I x capital I dV. Okay? This is what we're trying to do. Now, we realize that through the product rule of differentiation, this is simply the following. It is partial of I, sorry, it's Pi little I capital I W little I, okay, the whole thing gradient with respect to x, okay, so that carries an xi dV minus integral over omega naught partial of P little I capital I derivative with respect to xi Wi dV. Okay? This is the application of the product rule. Okay? Clearly. Right? Then what we do is to come along with the divergence theorem. Okay? And then we apply the divergence theorem on the very first, on the first integral on the right hand side here. Okay? When we apply the divergence theorem here by observing that because the little I index is being contracted out, what we have in parentheses here in that first integral is really a vector with free index capital I. Since we're differentiating it with respect to x capital I, we're effectively just taking a divergence of a vector which has free index capital I. So when we apply the Gauss divergence theorem to that first integral, we will essentially be looking at applying that divergence theorem to that vector. Okay? All right. So what that gives us then is that integral over omega naught P little I capital I derivative of W little I with respect to x capital I equals. Now the Gauss divergence theorem takes us to the boundary. And on the boundary we have Pii Wi, okay, the whole thing dotted with Ni dA, okay. And here we have the other term which was already defined as an integral over omega naught, which was of the form Now we had on the previous slide, if you recall, this term here, partial of pii little I capital I with respect to x capital I. This thing is essentially the divergence of p, the whole thing with index little I. Okay? So here we have exactly that term. Okay? All right, so when we put things together here, we observe that we get integral over partial omega naught. Now, this term, for the way we've been writing it, which it's better written as W dotted with P. Okay? That gives us a vector, free index capital I, and that is being dotted with N dA. And this is then, the last term is integral over omega naught, divergence of P dotted with W dV. Okay? All right. But now we observe something about it. So let's actually put it all together again. Right? So we have in our equation integral over omega naught minus divergence of P dotted with W dV plus, minus integral over omega naught BF dotted with W dV plus integral over omega naught, integral over the partial of omega naught over the boundary of W dot P, the whole thing dot N dA minus integral over the traction boundary T dot W dA equals 0. Now, I'm going to observe something about this. Okay? This boundary can be written as partial of omega naught displacement boundary union partial of omega naught traction boundary. Okay? I'm going to use that now. So that leaves us with the equation looking like this, integral over omega naught. Now, the other thing I'm going to do is that when we go back here, I'm going to club these two terms together because they are both volume integrals, right? So let's do that as well. So in my integral over omega naught is minus divergence of P minus BF, the whole thing dotted with W dV plus integral over the displacement boundary, okay, of W dot P, the whole thing dotted with N dA plus the same integrand but now over the traction boundary and then we have this over the traction boundary. Everything equal to 0. All right, so let's stare at this equation and let us look in particular at this integral. We observe that it is defined over the displacement boundary, and it also includes the variation over the displacement boundary. Now, when we defined the variation, we had a very specific condition for it over the displacement boundary. Okay? In particular, we said it has to belong to a space V, which requires that W vanish over the displacement boundary. Okay? Right? And there's another, right? So that's something we observe. What we can then do is first, so we observe that this term drops out, right? This very first this integral over the displacement boundary drops out because, okay, it drops out because W belongs to our space V. Okay. The other thing we're going to do is to club these two integrals then together. Okay. So we get integral over omega naught minus divergence P minus BF dotted with W dV plus integral now only over the traction boundary. Okay. I am going to write this term as W dotted with the vector Pn. Okay? And from here I get a minus t, right, from this term. I get a minus t. Okay? So, those last two integrals can be clubbed together in this form. dA equals 0. Okay? And now you should begin to see something. What you should begin to see here is that this term should look very similar to you to this one. Right? What I've just written out here is the balance of linear momentum. Okay, the PDE for balance of linear momentum. However, we are not looking at time dependence here, right? I made the point. I said that the equilibrium condition we got is also known as a weak form for static problems, right? It's a weak form of the balance of linear momentum for static problems. So if we ignore this term, right, or if we say that we don't have this, right, that we're ignoring the dynamic part of the balance of linear momentum, right? You see that the two terms in that integral are essentially the surviving members of the balance of linear momentum. Yes, the signs are different, but that doesn't matter, right? We can just multiply the balance of linear momentum through by a minus sign. Okay? You should also observe that what we have here is very much like our traction condition on the traction boundary, right? Our traction boundary condition on the traction boundary. All right?